understanding visual investigation patterns through digital field observations. The amount of data being generated by businesses today has grown to a point where manual analysis is no longer feasible. Many users are therefore turning to a growing variety of visual analytics products to help them explore and derive value from their data. To identify ways of improving these products, we need to have an understanding of what users are trying to do, their objectives, and how they use visual analytics tools to achieve their goals. However, the variety of data sets users operate on and the breadth of functionality these tools provide can make it difficult to reason about user goals and actions across domains. For example, do improvements that help a university researcher find repeating patterns in genetic sequences also translate to helping a business analyst predict customer acquisitions? A large body of past research has grappled with this problem by developing conceptual spaces, frameworks, models, typologies, and taxonomies to categorize user objectives and actions at various levels of abstraction. However, most of this prior work has been subject to several limitations. First, a majority used synthetic or non-domain datasets that participants had no prior expertise or familiarity with. These studies have also been with data of a limited size, on the order of tens to hundreds of megabytes, substantially smaller than what is encountered in large-scale business or enterprise settings today. Because many of these studies have been with experimental tooling or on non-commercial systems, participants have usually needed training with the product prior to or during the study, which may have affected their strategies and behaviors. Last, these studies have generally been performed in isolated and controlled environments. However, in enterprise and business settings, users generally work in a larger ecosystem where they can leverage other tools, resources, or people. They often work with disparate datasets that are inconsistently available between tools, and they usually have multiple responsibilities that reduce their ability to conduct open-ended explorations without a motivating goal or problem. These limitations lead us to the following research question. How does our current understanding of user objectives, actions, and how to support them generalize to an enterprise setting where a larger ecosystem of people and products might be utilized? To answer this question, we conducted two studies. The first was a digital field observation, where we remotely observed people doing their day-to-day work on PowerDrill, a visual analytics product, via video conferencing. We then analyzed usage logs of a different visual analytics product, which we'll call Data Explorer, of over 2,500 user sessions to test whether the findings from the first study were product-specific. Next, I'll briefly explain our method, followed by how we analyze the data and our results in the form of objectives, patterns, and emergent themes. We conducted 90-minute sessions with a 15-minute interview at the beginning to understand their objectives and 15-minute retrospective interview at the end. We had 9 full-time Google employees who regularly use PowerDrill for at least 90 minutes a week participate in the study, with 5 using it for more than 20 hours a week. These participants came from 8 different teams, performing visual analyses on domains ranging from production code to sales and accounts to travel to A/B experiments. The data they were working with ranged in size from tens of megabytes to hundreds of terabytes, with schemas that went from tens to thousands of fields. Next, I'll share a brief overview of how we analyzed our data and highlights of our results. If you'd like more detail, we encourage you to read the paper. For objectives, we transcribed what people described working on and paraphrased it to various levels of abstraction to find commonalities. Using this technique, we identified 4 common objectives across the domains our participants worked in. Some of these mapped directly to prior work. For example, investigating where and why data was not what was expected was very similar to the previously identified goal of identifying a main cause. Whereas determining if data signals matched known patterns had not been previously identified. We found participants only did this when they had extremely specialized domain knowledge and when their objective in analysis was something they had performed repeatedly, something you may not observe in a controlled lab setting. Next, let's take a look at how users achieve these objectives. To determine this, we manually created sequence models of all the keystrokes, mouse clicks, and other atomic actions. We then grouped these into 263 codes that fell into 20 categories. Examples of these categories might be visual analytics actions such as filter and zoom, or use of other tools like opening an email or looking up a person in the company directory. We then used these categories to visualize each investigation, then looked for common patterns. From these visualizations, we identified 6 patterns of investigation. We found 3 that supported patterns found in prior work. The first was the drill down, a series of progressive filtering, restricting, or excluding data to narrow the investigation space. The second was what we called the sawtooth, a repeated adding or removal of either the same filter or progressing down a list of filters. The third was the side-by-side comparison, which is the same as the compare pattern found in prior work. We also found 3 patterns that had not previously been seen in prior work. The first was the side step, where after drilling down, a user would remove almost all of their prior filters, except for the most recent, to see if data patterns look the same with only the last filters applied. The next was the fan out, when a participant would open multiple new branches of investigation simultaneously, often by creating new tabs. They would later iterate through each tab, often performing the same analytic steps in each, before closing branches that weren't promising. And finally, the plug and play, which illustrates when participants loaded a previous investigation, either their own or someone else's, from a template to save time, where the visualizations needed for the investigation were largely already there and they just needed to change out a variable. Next, I'll highlight 5 unique themes that we identified related to the way participants collaborated and interacted with their larger product ecosystem. Unlike many prior studies that occurred in isolation, we were able to observe that a majority of analyses actually leveraged prior work, both as a starting point and as a reference during investigations. We found that real-time collaboration was a crucial part of some investigations, with 3 participants pausing or switching to a parallel work stream while waiting for help from someone else. We also found that 5 of the investigations involved direct review of another person's analysis to verify that they would reach the same conclusions. As far as ecosystem themes, all of our participants described an intention to act on their findings or performed follow-up actions during the session, highlighting that insight generation was not an objective in and of itself. We also found that products outside of the visual analytics tool were crucial. We observed that participants leveraged 53 products outside of PowerDrill to do things like orient themselves to their investigation, document and share findings, or look up and ask others about business logic. Next, Feng will talk about how we analyze logs from Data Explorer, a different visual analytic product, to validate our observed patterns.
Thank you, Irene. To validate how frequently patterns were used in each investigation, we conducted a log study with over 2,500 user sessions from Googlers and used an algorithm named closed fast to mine frequent patterns. Let's look at the findings. We used the heuristic rules to identify patterns. For example, for drill down, we checked if there were repeated actions, and the figure shows that it had 12 actions of field editing with support of 1209. We also found other 4 patterns by the algorithm, including plug and play, sawtooth, side-by-side, and fan-out. However, sidestep was manually identified as its support was low. As a summary, we found that 5 of the 6 patterns were validated, while sidestep was manually identified.
We described a field observation of 9 Google employees from 8 different teams doing their analyses in PowerDrill to identify 4 objectives, 6 recurring patterns, and 5 emergent themes. We also described an analysis of Data Explorer logs to validate that the patterns we found weren't product-specific. Our work had several limitations. The products and participants were all within the Google ecosystem, so whether the results are generalizable to other ecosystems or populations is an open question. Our manual sequence modeling may have led to some inaccuracies, and some details for the study were proprietary and had to be omitted from this work. However, we believe our findings may be applied to future efforts to predict user behaviors or guide users to their objectives more quickly. They also suggest a need to consider how real-world analysis behaviors within a larger ecosystem may differ from what's observed in isolated study conditions. With that, we'd like to thank you for listening, and thank you for your attention.